Okay, and by this formula we can make the differential of the energy for frequency and differential of the momentum for wave number, and we can obtain the forms like this. Okay, you can see the differences between this form and this form. Okay, in the right side, these are the forms usually used uh, in ordinary inscription in the quantum wave picture, which Lorentz factor cannot appear explicitly, but I want to make the Lorentz factor appear explicitly, such as in a particle picture. You know that for a particle picture, when we make the differential of the energy for a velocity, we can get explicitly that the Lorentz factor appears with the gamma order 3. Can be look for the uncertainty formula for energy and momentum in particle picture. I want to make the equivalence between a particle and wave picture, but it is easier than we look at the problem in the particle picture. Also, between the particle and the wave picture have the same meaning to describe about a quantum phenomena. And then we can get the relationship between the differential of the energy and differential of the momentum like this. Okay, inside the brackets, it is now as the group speed. And then this group speed relates between the uncertainty of the momentum and then the uncertainty of the energy. We know that omega c defined omega 0 as the coefficient of c. You know that c is the speed of light, and this coefficient can change from 0 to 1. This can be 0 when the omega p is 0, and this can be 1 when the omega p is equal to omega 0. Okay, so in this condition, when omega p is close to omega 0, so the coefficient of the c is close to 1, and it means that close to the speed of light. And then uncertainty of E and uncertainty of E is related by the group speed is close to the speed of light. Okay. Okay, next. In the right side of the total energy differential, there is the term inside the bracket. You know that the term inside the bracket is a quotient from this differential. And in fact, that the term inside the bracket is the same form when we make the differential of the non-relativistic kinetic energy. This is the formula for non-relativistic kinetic energy. We write like this, and we have modified to be like this. And when we make the differential of the non-relativistic kinetic energy respect to the differential of the frequency, we can get to form of a differential that is same with the term inside the bracket, which is a quotient from the differential of the total relativistic energy. This is exactly the same form. So we can understand that the term inside the bracket as if the non-relativity kinetic energy uncertainty. Also, this term is gotten by derive this energy respect to the frequency. Okay. the total relativity energy, and the right side as if the uncertainty of non-relativistic kinetic energy that don't have the Lorentz factor. And we can rewrite above formula to below. Delta E is equal to gamma order 3 times delta K phi. And then for momentum, this is the uncertainty of relativistic momentum. When we make the differential of the formula of relativistic momentum with respect to the wave number is like this. Okay, we can get this term inside the bracket. You know that the term inside the bracket is the same as if we get the uncertainty by non-relativistic momentum. When we make the differential of a non-relativistic momentum to the wave number, we can get the form of the uncertainty is the same form like the term inside the bracket. You know that the term inside the bracket is derived from the relativistic momentum, so that we can understand that left side is the uncertainty for relativistic momentum and the right side is the uncertainty in our purpose to the non-relativistic momentum. Okay, it is clear. As if the uncertainty for non-relativistic momentum, and this is as if the uncertainty of non-relativistic kinetic energy. Okay, and when we see the pictures, this is the pictures. The uncertainty of the relativistic energy is bigger than the uncertainty of the non-relativistic kinetic energy. And between this uncertainty, there is the Lorentz factor. And when the uncertainty of the kinetic energy increase small, the uncertainty of the relativistic total energy is increase larger because of the increasing the Lorentz factor. It is happen also in momentum. This is uncertainty of relativistic momentum is also bigger than the uncertainty of the non-relativistic momentum, and is related also by the Lorentz factor. And when there is a small change or the uncertainty non-relativistic momentum, it can give the impact that the uncertainty of the relativistic momentum will be increased larger than the increasing of the uncertainty of the non-relativistic momentum because of increasing the Lorentz factor. And you can look at this picture is the distribution function in the momentum and energy line. And then I will make also in the domain of position. Of this, we can express to you that in the web description, the Fourier component of the uncertainty of the relativistic energy and momentum is more compact. This is many more the Fourier component which superpose each other to form the wave packet. This is wave packet. This is many more than the superposition. You know that this phenomena, the first phenomena, is the superposition of the Fourier component with the Lorentz factor. But the second phenomena is the superposition of the Fourier components without the Lorentz factor. Okay, we can decide that the Planck constant is the natural constant in this problem. Because of that, we can remove the Planck constant and we can understand that the Lorentz factor as the coefficient of this term and these terms and can relate this understanding with this understanding. We can also remove the Planck constant and we just leave this term. You can imagine that when the Lorentz factor times the uncertainty of the frequency, and this is also Lorentz factor times the uncertainty of decay, where in this uncertainty there is no Lorentz factor, and also in this uncertainty there is no Lorentz factor. This Lorentz factor can make this uncertainty bigger than this uncertainty, and it is also Lorentz factor can make this uncertainty is bigger than this uncertainty. And as the consequences, the Fourier component is much more in this superposition than in this superposition. Okay, you know that superposition with a Lorentz factor is proposed to the superposition of the uh, relativistic quantum phenomena, and then the superposition without the Lorentz factor. Uh, that is the superposition which proposed to the case of the non-relativistic phenomena. And for this superposition phenomena, we can get the wave packet. Look at the wave packet between superposition in relativistic and non-relativistic are different. And okay, maybe you suppose that this wave packet is moving with the speed close to the speed of light, and this wave packet is moving with the speed is lower than the speed of light. Okay, you are true, but I will explain a detail the differences of both wave packets. Okay, I don't yet explain to you how much the numerical velocity of both wave packets. And because of removing the Lorentz factor, it is give the understanding that between this wave packet and this wave packet, although the form of both wave packets are different, the numerical speed of both wave packets are same. Okay, the speed of this wave packet is close to the speed of light, and it is also we can just understand that because of removing the Lorentz factor order 3 from equation above to the equation below, just alter the form of the wave packet from the form above to the form below, and not alter the numerical speed of the wave packet. The numerical of both wave packets are still same. This is close to the speed of light, but but this there is no in reality. We really can imagine that this relativistic and this non-relativistic, when this numerical speed is lower than the speed of light. Okay, so we can really get the understanding and description that this is truly for non-relativistic and this is truly for relativistic.